Welcome back, Super Friends. Today we are going to do part 2 of our Unit 13, 14, 15, 16 review. You will need your packet, a pencil to write with, and don't forget that super brain of yours. Stay tuned for the video. All right, Super Friends, we are going to finish up our review. This is part 2. Question 15, the points on the coordinate plane show in Lillian's town. So looking at the table, I see there's a bus stop, a library, her home, and a store. Lillian moved from one place to another by moving down 5 spaces and left 7 spaces. Which way could she have moved? So if we're going down 5 spaces and left 5 spaces, I need to see exactly just start at each one. Or we can even go through the options. So if we want to start from library to the store, let's see. Library, if I go down 5 spaces, I'm off the map. So I know that won't work. From home to the bus stop, let's see. 1, 2, 3, 4, 5. And then left 7. 1, 2, 3, 4, 5, 6, 7. That brings me right here. I don't believe that's correct. That's from home to the bus stop. That doesn't take me to the bus stop. Let's try from the store to the library. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. That did get me to the library. So let me double check from home to the library just to be sure. If I did this again, 1, 2, 3, 4, 5. Again, that doesn't get us to the library because we just did it. So the only option is this one. All right, let's do number 16. The location of William's school is represented by the point on the coordinate plane below. William left his house, walked 3 units down and 2 units left, and arrived at school. What is the location of his house? So for this question, we want to go the opposite because it's like saying he's at school, but he started somewhere else. So where did he start if this is the finish? He finished here. Where did he start? So what you do is you do the opposite. So instead of going 3 down, we would go 3 up from the school. Instead of going 2 units left, we would go 2 units right of the school. So let's do that. So I'm going 3 units up. So that is, start at here, 1, 2, 3. And then instead of going left, I go right, 1, 2. So this point, where's my X? Where's my Y? My X is 6, my Y is 7. X, Y. So that's where his home is here. Let's see if we see that point. Yep, we see it, 6, 7. Okie dokie. Let's go to the next example. All right, next example says the table below shows the first terms of the patterns with 2 different rules. Rule A is multiply by 2 and starts at 1. Rule B is add 2 and starts at 2. So they already made us a table, so I'm going to go ahead and use their table. If you didn't want to use their table, you could say Rule A, you could say Rule B, and then you would go from here. So 1, 2, and this is multiply by 2. And this is add 2. So if I'm adding, or if I'm multiplying by 2, the next one would equal 2. Then 2 times 2 is 4. 4 times 2 is 8. One more, 8 times 2 is 16. Okay. If I'm plussing 2, 2 plus 2 is 4. 4 plus 2 is 6. 6 plus 2 is 8. 8 plus 2 is 10. So now it says, for which term is rules A number equal to rule B? So if we just wrote these in, so for the A, I had 1, 2, 4, 8, 16. For B, I had 2, 4, 2, 4, 6, 8, 10. Which term has the same number in it? That is term 4. The 4th term has 8 and 8 inside of it. That's how we would do number 17. Let's look at 18. Hannah uses the terms from two patterns to form ordered pairs to plot on a grid. Both patterns start at 2. So both start at 2. The rule for X is to add 1. The rule for Y is to add 3. Okay, and then it was just saying which of these options would be one of her pairs. So if we were doing this, this would be the ordered pair for this one. It would look like 2, 2. All right, so add 1, that would be 3. Add 1, that would be 4. Add 1, that would be 5. Add 1, that would be 6. And I'll stop there. Now over here, add 3. 2 plus 3 is 5. 5 plus 3 is 8. 8 plus 3 is 11. 11 plus 3 is 14. Stop here, and I'm going to make my points. The second one would be 3, 5. This one would be 4, 8. This one would be 5, 11. This one would be 6, 14. Okay, let's see if we have any of these that we can bubble in. I see 3, 5. I don't see 4, 5. I don't see 4, 6. I don't see 5, 3. So the only thing is 3, 5. And that would be an ordered pair that Hannah would plot based off her information. All right, let's go to the next examples. All right, example 19. The graph shows the relationship between the amount of time and the number of push-ups Eric did. So looking at this, I always like to go in and plot the pairs that I see here. So this first one is obviously at the origin, which is at 0, 0. The next one is right here. It looks like it's between the 10 and the 5. So I would say 115. So that's 115. This next one would be 230. 230. The next one here looks like it's between 40 and 50. So that would be 45. And then that's at 3. So 345. And then our last one right here is at the 60. So that'd be 460. Okay. So we have all of them plotted now, or all of them labeled. Which statements about the graph are true? So let's look at the first one. Eric can do 15 push-ups in 1 minute. So we see that the time is down here. That's the minutes. And then the number of push-ups is the Y. So for 1 minute, how many push-ups do we have him at? We have 1 for 15. Yeah, so that's true. This is correct because at 1 minute, he did 15 push-ups. So let's look at the next one. It says the next ordered pair on the graph would be 570. So if it's saying every minute he does 1 push-up, every minute he does 15 push-ups, then we would just add 15 push-ups to the last point that we had here. So we were at 460. The next one would be 5 what? What's 60 plus 15? That'd be 75. So no, it wouldn't be 70. It would be 575. Close, but not true. All right, let's look here. It says 0, 0, 115, 220, 335, and 460 are all points on the line. Let's see. 220 is right here. Is that on the line? No. 335 is right here. Is that on the line? No. So they are not on line. Okay. Now it says divide the number of push-ups by 15 to find the number of minutes. So if we did that, let's try the 30. So 30 divided by 15, will it equal 2? Let's see. How many 15s does it take me before I get to 30? Let's do my 15s facts. Oh, it would take me 2, which equals 2. So yes, that's true. Because 30 divided by 15 equals 2. That is true. Okay, now the next one says multiply the number of minutes by 10 to find the number of push-ups. That's not true, because if we did for 1 push-up, he does 15, or sorry, for 1 minute, he does 15 push-ups. So if we did 1 minute times 10, that wouldn't give us 15. So no. It's not 1 times 10, it's 1 times 5. So you multiply or 1 times 15. You multiply the number of minutes by 15, which is the next one. Yep. So not by 10, that's not true, but by 15, that is true. And then it says multiply the number of push-ups by 15. That's not true. We're not multiplying the number of push-ups by anything. We're multiplying the number of minutes. We multiply by minutes, not by push-ups. Okay, so that last one is not true. The only ones that we have here are the first one, D, so it's A, D, and F. That's what we have here. All right, let's go to the next examples. Okay, question 20. Kim and Rachel are creating patterns. So it's just me making my pattern. It says, what is the first number in Kim's pattern that also appears in Rachel's pattern? So I'm going to have K for Kim, R for Rachel, and then we're going to start. So Kim starts at 3, Rachel starts at 2. Kim is multiply by 2, Rachel is add 5. All right. So for these, I know sometimes I can go really long, so I'm going to try to give myself as a lot of spaces as possible. So 3 times 2 is 6, 6 times 2 is 12, 12 times 2 is 24, 24 times 2 is 48, 48 times 2, that is 16, 1, that's 96, and I'm going to stop there. Let's go to the next one. 2 plus 5 is 7, plus 5 is 12. Ooh, hooray! We didn't have to go too long for this one. So 12 and 12 are the same. So that's our answers. We bubble in 12. That was a number that was the same. Okay, let's look at number 21. Lori and Max are creating patterns. The first term in both patterns is 2, as I see here, where it says Lori's pattern, Max's pattern. Lori uses times 2, subtract 1. Ooh, Lori's getting tricky out here. Times 2 minus 1. And Max is just using plus 6. So we're just filling in the answer choices. So I'm guessing I'm filling in the number for the square, filling in the number for the triangle, filling in the number for the circle X. That's what we're doing. Okay, so if I'm doing 2 times 2, that equals 4, minus 1, that equals 3. So that's going to be 3. And then let's keep going. If I do 5 times 2, that's 10, minus 1, that's 9. So this equals 9. Okay, then let's do the triangle. 2 plus 6, that equals 8. Good job. All right, let's bubble it in. So the square is equal to 3. The triangle is equal to 8. Sorry, I messed up. Triangle is equal to 8. The circle square is equal to 9. Yep, and that's how you do it. Let's go on to the next set of the examples. All right, question 22. Select the shapes that always have 2 pairs of parallel sides. Remember, parallel looks like across the street, right? So it looks like a sidewalk. It could be like this. It could be like that. It could be like this even, because those are still across the street. Okay, so let's see which ones have 2 pairs of parallel sides. I know square has 2 pairs of parallel sides. Correct. A rhombus, remember rhombus is like a sideways square. Those also have 2 sets of parallel lines. Rectangles, we know that rectangles have 2 pairs of parallel lines. Trapezoid, in the notes for trapezoid, it says it's only 1 set, not 2. So trapezoid is no, because it only has 1 set of parallel lines. Quadrilaterals, this is always, right? Remember, quadrilateral is all 4-sided shapes, even trapezoids. So can we say that always a quadrilateral is going to have 2 sets of parallel lines? No, because sometimes they're going to be trapezoids. So we would say sometimes, not always. And then lastly, a parallelogram. The definition of parallelogram is that it has 2 sets. So yes. Hooray for a parallelogram. So those are the ones that have 2 pairs of parallel sides. Number 23. Which statement below is true? A rhombus is never a parallelogram. That's not true. A rhombus is always a parallelogram because it always has two sets of sides that are parallel. A polygon is always a quadrilateral. No, that's not true. What about triangles? So no. Sometimes it is sometimes a quadrilateral because we have all other types of polygons. We have 3-sided, 5-sided, 6, 7, 8, all of those. Now let's look at the next one. A square is always a rhombus. That could be true because remember, rhombus is where you have opposite sides that are parallel and they are the same size, and that's everything that a square is. So we're going to put a yes here. Let's check the last one. A rectangle is never a square. That's also true. Oh, so we can't well, a square is always a rhombus. A rectangle is never a square. Okay, so in this case, it's going to be a square is always a rhombus because a rectangle is sometimes a square. Because remember, squares can be rectangles. That's the way I'm reading this. So I'm going to say sometimes. Okay, but a square is always a rhombus because it means the same thing. Square and rhombus mean very similar things. The only thing that a rhombus doesn't have to have is the 4 right angles that a square is. So that would be the only reason why we wouldn't do that. Okay, let's move on to the next set. All right, all parallelograms have 2 pairs of parallel sides, and all squares share all the attributes of other quadrilaterals. Which of the following shows the placement of the quadrilateral names so that if it represents the correct relationship between the types of quadrilaterals? Okay, so this was read really crazily. They're just saying which of these Venn diagrams and graphs show correct information. So looking at it right now, it's saying that in a square is always a rectangle, always a parallelogram, and then always a rhombus, right? But then it's also saying that a rectangle is different than a rhombus and that the rectangle is different than a parallelogram. That's not true because all those things, a square, rectangle, and rhombus, are all parallelograms. So this wouldn't be off. That wouldn't be true. Let's look at the second one. It says parallelograms. They can be rectangles, they can be rhombus, and then the square would be both a rectangle and a rhombus. This one, it looks pretty good because I do know that a rectangle or a square can be a rectangle and a square can be a rhombus. And I know that a square is a parallelogram. Okay. Now, again, C looks like B or C looks like A, where it's saying that you can't have a rectangle, a square, and a rhombus all be parallelogram, which that's what it should say. So this one's not saying the correct stuff. The last one, let's see. Okay, so it has it all being a parallelogram, which is true. And then it says that rectangle and square are different, but that they could sometimes be considered both for a rhombus, which that's not true. The only true way is if the square was here. If the square was there and the rhombus was there, that would be true. But in this case, it's not true. So this is our answer, where it has parallelograms that could be rectangles and parallelograms that could be rhombus, but it's saying that a square is both a rectangle and a rhombus, which we do know that. All right, next set. All right, these are our last questions that we're going to do. Which of these classifications of a triangle are possible? Both words in the description must apply. So that's saying, like, remember, we have words. I'm going to say angle. Oh, no. Oh, no. Remember, we have angle words and side words. So remember, the sides can be scalene, because that means that the sides don't equal. It could be isosceles. That means that 2 of the sides are equal. It could be equilateral. That means all of the sides are equal. And then for the angles, it could be acute, a right angle, or an obtuse angle. And remember, you can never choose 2 in one instance. Actually, that's not true. In some of these cases, you can't choose two. You can't say, oh, that triangle is a scalene isosceles. That won't work. You can't say it's an isosceles equilateral. That won't work. But in some cases, you could say, no, you can't. Not for a triangle. You can never say that the triangle is an obtuse right triangle. That won't work. Okay, so let's look at them. So can we have a right obtuse triangle? No, we cannot. It would just be either called a right triangle or an obtuse triangle. It cannot be both. Could we have a scalene right? Yes, we can. Could we have a scalene obtuse? Yes, we can. Could we have an isosceles acute? Yes, we can. Could we have an equilateral right triangle? No, we cannot. Because if we're doing a right triangle and have it equilateral, actually we could. Do these all look the same side? I think it's possible. Maybe it is possible. Let's hold out on this one. We'll say a question mark. I'm not sure if it's possible yet. All right, let's do isosceles scalene. We cannot. Equilateral obtuse, that one I know we definitely cannot. Like, there'll never be an instance where it's like, yeah, I can't even draw it. This is obtuse. No, because this side is smaller. This one's smaller than these two. Yeah, that won't ever work. And this is an obtuse angle. Nope. So that won't work. Okay, so I think there is an instance where we can have a equilateral right triangle. So we're going to say yes, but these are our yeses. Yep, and the rest are no's. Okay, let's look at number 26. The Venn diagram shows that some properties are shared by rectangles and rhombuses. Which shape belongs in the overlapping section? Remember, it could be both. We should know this by heart by now. Which shape is both a rhombus and a rectangle? Obviously, a square. The square goes in there. Yep, that's a parallelogram, that's a rectangle, that's a rhombus. The square goes in there, square. All right, that was it. Okay, these are our notes. These are the second half of the notes to help us prepare for our USA. Go ahead and use these notes to help you answer your questions.